Good evening to all. My name is Eleftherios Petavratzis, and I am PhD candidate at the Laboratory of Nonlinear Systems Recursion Complexity at the Department of Physics of Aristotle, University of Thessaloniki. Today, I would like to discuss about the topic that we are currently working on, which is based on the chaotic motion control of a mobile robot using a memory technique. With this presentation, first we will talk about the chaotic dynamical systems. Then we'll talk about autonomous mobile robots, and we'll introduce the notion of the path planning. Then we'll construct our main method, which is called a memory technique. And finally, we'll have some conclusions according to the results that the simulations present, and maybe a future work that will be done. So, what is a chaotic system? The definition is very simple because it is a dynamical system that is governed by a deterministic law and is very sensitive to initial conditions. That means that even a slightest change in its initial condition or parameters could force it to present a different behavior. Here you can see two very simple examples of chaotic motions, and you can see that even with the same position, with the same starting position, we have a complete different behavior. The tools for studying the behavior of chaotic systems are the verification diagrams and the Lyapunov exponents. The verification diagrams are diagrams that can show us in which areas the system shows periodic or chaotic behavior. In this case, we have the diagram of the logistic map, and we can see that from the 0 point until 3.5, the system has a periodic behavior. And after that, and until 4, the system goes to chaos. The Lyapunov exponent shows the same way with the same result with a different way. If the Lyapunov exponent is negative, then the system is in periodic state. And if the exponent goes to positive values, then the system has a chaotic behavior. So what is an autonomous mobile robot? There are robotic systems that are performing tasks without the presence of a user. Their use is very crucial for space missions, in fires, and other military missions, such as scanning an area for explosives or dangerous materials. Here you can see some examples of these systems, and maybe you can recognize the vacuum cleaning robots and robots for space missions. Of course, there are many others. And in all these missions, the robotics systems should achieve three main goals. First of all, the perception and the identification of the target. Secondly, the knowledge of the current position of the robot. And finally, the robot should update the terms map. However, the most important thing is the path planning. Path planning is a strategy for moving a robot from a static to an ending position. In patrolling missions, the robot should find a plan to achieve three main goals. First of all, it should scan entire the terrain. Secondly, it should create an unpredictable trajectory. And finally, it should scan the given space as soon as possible. All of these goals could be achieved, as I said, by using chaotic dynamical systems. In our case, we want to create a random-like motion sequence using a chaotic system and a model operator. And secondly, we want to create a strategy for incomplete and fast scanning of a given area based on the use of the memory element. In literature, there are different kinds of chaotic systems. They have been grouped in two main categories, discrete and continuous, and their uniqueness relies on the fact that they are very sensitive on initial conditions, as I said before. Here in this work, we have used a two-parameter discrete map which is called a modified logistic map. The form is over this, as you can see over there. And after that, we decided to use these kind of parameters in order to produce the results. Next, we wanted to produce basic commands for controlling an autonomous robot. And in order to do that, we use a model operator, as you can see over there, which took the integer part of this argument and transform it into basic commands according to this simple rule. After that, we took the histogram of 1 million values in order to see if there is an equal chance of producing the motion commands. And you can notice that indeed we have this behavior. After that, we wanted to create the memory technique, which is very simple. First of all, the robots, according to this method, the robot computes the number of visits in it for adjacent cell. Then, if there is according to this method, if one of these cell has the least number of visits, then the robot moves to this cell. Otherwise, if there are two or more cells with the same least number of visits, the robot uses the motion commands in order to move it to one of these cells. Here we have some results according to the coverage performance of memory-free and memory technique. And you can notice that there is a big difference in these two methods. In these figures, we decided to give many more motions, but the results are quite the same. Also, here you can see the numbers of visits in each cell for the memory-free and the memory technique. And you can notice that in the memory-free area, there are multiple visits in same areas. But in memory technique, this behavior is reduced, is improved. Also, we have decided to insert two obstacles, and you can see that the behavior hasn't changed anything a lot. Here we have gathered the results for the coverage rate according to the number of iterations. And in the second figure, you can see the mean visits per visit cells according to the same number of interactions. In these two figures, you can see that the memory technique shows better results both in coverage rate and in mean visits per visited cell. So to sum up, the robot uses a local optimization in order to select the next cell that will move. The memory technique improves the coverage rate and reduces multiple visits in each cell. And of course, as a future goal, we can see that we can use a different kind of chaotic systems in order to study the behavior of the robot. And finally, we wanted to implement the proposed method in real robotic systems in order to see and deal with the positive challenges. Thank you very much and stay safe.